Hello everyone, thank you for joining me. This is a fun little browser game I came across about a week or two ago called Nandgame. It takes you through step by step the circuits and components that are involved with building a computer. So I figured I'd go through all these levels step by step and give a bit of insight from an electrical engineering perspective. I myself am an electrical engineer. I've got my master's in electrical engineering and I'm working as a consultant for the renewable power industry. So without further ado, let's get into it. So our first step is to build this NAND gate. And what a NAND gate does is takes two inputs, A and B, and will send power to the output for all states except for when both of these inputs are on. And so we've got these two components here, which are called relays. And how these components work is we've got this coil of wire here and an iron core. So when a voltage is applied, this coil of wire, which is usually called an inductor or a solenoid, will create a magnetic field around, which will pull this bar down, completing the circuit on this side. You can see how that functions here. When B is on, it's sending power through that switch, but because there's no complete circuit, the power doesn't go anywhere and no current flows through the system. But when we have A activated, it runs current through that solenoid, which pulls that bar down, allowing the circuit to complete and power to flow. But this is incomplete here because if we connect the output here, for instance, it's not really doing what we want it to do here. Luckily, we have this other input here, which is a constant power input. So if we add another relay here, that is always on. You can see that the circuit is completed automatically. This is what's called a normally closed switch, where this would be normally opened. So if we see here that when these both inputs are on here, this value will be on, which means we can send power to the solenoid here, bringing that switch down and turning this off, which satisfies all the conditions here. Now, in the real world, I'm sure relays were used in very old computers. In fact, that's exactly what they were used for, relays and vacuum tubes. But in the modern era, these are typically made with transistors. And the reasons for that is transistors can be made very, very small. You can use a whole lot less power activating transistors than you could with relays. And also relays had this issue where the power was too high when that switch went down, and there's a split second where the gap is small enough for current to jump over. It got a little bit of a shock there, which the heat generated from that can actually melt the switch to that terminal. Uh, and so for all those reasons, transistors are, a much easier way to build these components from now on. So let's move on to components used, simplest possible solution. Next. So now we have to build an inverter. And all this does is takes whatever input you have and it gives the opposite to the output. This should be fairly simple with our NAND gate here, because if we treat the single input as both inputs, we know that this will turn off when both of these inputs to the NAND gate are on. And you can see, works exactly as intended. Let's bring that to the output there, and it works. Let's move on. Now we have an AND gate. So this is simply done by taking your NAND gate and inverting the output so that it functions in accordance with the logic diagram here. So we can see when both are off, the output is off, and when either switch is on, it's still off, and only when both switches are on, the NAND gate turns off as we expected, And because the input to this inverter is 0, the output will be 1, and that satisfies our solution. Next level. Now we go into an OR gate, and this functions where instead of both inputs having to be on, or both inputs having to be the same state on or off in order for your output to be on, any one of these inputs or both of these inputs could be on, and the output will be on as well. So let's take our NAND gate here, and let's just take a look at what we're doing here. So we have both inputs are off, and our output is on. And every situation, or every combination of inputs except for when both of these inputs are on, the output will be on as well. It's only when both inputs are on that the output is off. And we can see that this is pretty much the exact opposite condition with our OR gate. For instance, if we were to take these input values in this table here and just invert them, we would have the same behavior as our NAND gate. And so it makes sense that all we need to do here is invert our inputs and we have our OR gate. Any one of these inputs could be on, both of them can be on, and the output is on, and it is only off when both inputs are off. Let's check this. Good. Let's move on. Now we have an exclusive OR gate, or just denoted XOR. This is a variation of the OR gate where only one of these inputs can be on for the output to be on. If both inputs are off or both inputs are on, then the output is off as well. So we can see this. Let's first just connect the output up. Let's just look at the conditions where it's on. If A is off and B is on, then it's on. Or if A is on and B is off, then it's on. That gives us an idea here. We can take these conditions and give their corresponding gates here. So you have a condition where A is off and B is on. So let's put B on here. And let's invert A so that when A is off, one of these is on. So if A is on and B is on, that won't work. But if B is on and A is off, that satisfies this condition here. So that's halfway. Let's just put this over here so we can clear the area a bit. And we're going to do the same with A. If A is on and B is off, that should work. If A is on, if B is on, if A and B are on, it's off. So that works for the exclusive OR gate. Let's just check this here. Okay, it works, but it's possible to use this using fewer components. So let's try to figure that out here. What I'm going to do is I'm going to give some space here for these components, and I'm going to turn them back into AND gates by this replace with parts section. And let's see. Let's do that with the OR gate as well. This with parts. Let's try to keep things close together so that it's not too cluttered, although it kind of seems pretty cluttered now. Let's see. Okay, so we can already see an issue here. We have two inverters here, and all that does is just gives the same input as this NAND gate. So we can bypass both of these and delete these inverters, and it has the same overall function. And what this also does, if this was a real-world system, each component here, when broken down into its base components of transistors, has some delay associated with it. So, for example, let's say these were like 10 nanoseconds. That's like an infinite amount of time as far as like computers are concerned now with today's technology. But let's just assume it takes 10 nanoseconds to go through this NAND gate, this inverter, and this inverter before it finally gets there. That's a huge delay there as it stacks up, with two of these being like a 20-second delay here. So we can just get rid of that altogether and bypass it, and it still works. So now we know if we cheat here and look at the logic gate, we see it works, but it's fun to just go through it yourself and see how it does. Let's see how we're doing now. Okay, we got it down to 5 NAND gates total, but we can still use fewer components. Let's see. See what we can do here. So, if you can see what I see, these two NAND gates have a very similar purpose, and it's so similar that we can actually replace it with a single NAND gate for each input. That way. So these two are both 1, and if we turn one of them on, if we connect it like this, you can see it still has the same functionality to it. B is always on so long as A is off. Then when A turns off, A and B are on. This branch turns off, allowing this branch to go. That affects here to allow A to be turned on here. And same thing for the other side. So this still satisfies the exclusive OR gate. And I think that is as simplest as we can go. Let's check it out. And yep, there it is, the optimal combination, or the optimal use, optimal number of components. So that is our logic gates.